Good morning, everyone, and welcome to our session on geomechanics and its application in the Permian Basin. My name is Mayar Torre, SP International member, and I'll be your moderator for the next two sessions. Before we begin, I'd like to remind everyone to keep the chat box professional and respectful, focusing on the topic at hand. Let's maintain a high level of discourse and make the most of our time together. Now, let's get started. I'm honored to introduce our esteemed speaker, Karim Zaki, who currently serves as the Geomechanics team lead at Chevron in Houston. With over 2 decades of experience in the industry, Karim has established himself as a leading expert in geomechanics with a proven track record of driving innovation and excellence. Karim's impressive career spans roles at Advantic, Chevron, and various industry-leading organizations, where he has made significant contributions to the field. He has authored 41 papers, served as an SP Distinguished Lecturer, and holds multiple patents for his work. His expertise has been recognized with prestigious awards, including the Chevron Subsurface Excellence Award. Today, Karim will share his insights on leveraging geomechanics to optimize operations and drive sustainability in the Permian Basin. We are so privileged to have him share his expertise with us, and I'm looking forward to a thought provoking discussion. Please join me in welcoming Karim Zaki. Thank you so much for coming today, and the mic is yours.
Thank you, Mara, so much for your lovely introduction.
Thank you.
I'm very happy to join you guys here and have this discussion. Hopefully, you guys will find it interesting. So I'm going to concentrate on subsurface integrity, right, which is a major risk when we're talking about injection. Specifically, I'm going to focus on injection of CO2 for storage, but you can also take a lot of these concepts and apply them to water management in the Permian, which I know is a big issue. So there's a lot of overlap between these different components. So first of all, I just want to thank my team. So this is basically a representation of the Chevron Geomechanics Center of Excellence with our management. We have two teams. I'm one of the team leads, and then there's another team lead also that works with me. And overall, we have about 22 different contributors to this presentation, and also to the role of geomechanics as it pertains to subsurface integrity. So from there, geomechanics it was quickly recognized in Chevron as a critical component that delivers across multiple aspects of Chevron's business value. So with geomechanics, we enable safe operations and reduce environmental risks, right? So we're looking at drilling hazards, we're looking at production or injection hazards. Specifically today, we're going to be looking at injection issues relating to carbon sequestration and estimation of things like worst case discharge. So worst case discharge, think of sort of issues like Macondo in the early 2000s. Those would be issues that the geomechanics team would be involved in. And that relates to Chevron's tenet of operation, which is always operate in a safe and controlled condition. We've also expanded geomechanics, and we're looking at enhance field productivity and ensure reserves, right? A lot of you will be familiar with the concepts of hydraulic fracturing and the roots of that technology within geomechanics, and understanding the dimensions of the fractures and how the material properties such as modulus, Poisson's ratio, stress, and pore pressure impact the fracture geometry. So that's another key aspect of what we do as a group. We also take those same learnings and we apply them to deep water assets or carbonate assets or other different types of assets all over the world. And that speaks to our fifth tenet of operations here in Chevron, which is always meet or exceed customers' requirements. And the third component of geomechanics is safeguard the system integrity and reliability. And really the difference between safe operations and system integrity here is when we're looking at safe operations, the impact is typically in either on personnel or environment. When we're looking at system integrity, we're looking at equipment and deliverability. So when you're thinking about these types of aspects, you're thinking about aspects of wellbore integrity, the ability of the wellbore to deliver production or deliver injection over a sustained period of time. So that speaks to Chevron's sixth tenet of operation, which is always maintain integrity of dedicated systems. So through this presentation, the objective that I'll try to sort of communicate is how do we ensure subsurface integrity associated with CO₂ sequestration. And as I said, you can replace CO₂ sequestration here and also think about aspects of water management and water disposal, which is, again, a big aspect of what's happening in the Permian. So first of all, we have to be able to define the risks. We have to be able to develop a plan to assess the risks, monitor the risks, and modify execution as necessary to either remediate or mitigate these risks, right? So understand what the risk is, understand how you're going to measure it, understand how you're going to quantify it, and then understand how are you going to develop plans to mitigate that risk over a sustained period of time. So before that, we want to sort of define in the subsurface, what are we talking about, right? So we're talking, when we're setting up a model, we're trying to understand, or when we're setting up an assessment of subsurface integrity, we're trying to understand what are the different components, what are the different parts of the earth or the subsurface that we're concerned with. Typically, when we're looking at production, we focus on the reservoir solely. We're focusing on understanding the reservoir and it's the specifics of the reservoir. When we're looking at subsurface integrity, we're looking at understanding 4 different regions. We're looking at understanding the injection zone or the reservoir or the aquifer that we're producing and injecting into. We're looking to understand what's happening beneath it or below it. Do we have faults? Do we have things that could be moving below it that can cause issues? We're looking to understand what's happening directly above it, and we refer to that as our containment zone. So we have our injection zone, below it underburden, above it, immediately above it, our containment zone. This is the zone that we're going to look at to seal the aquifer or the reservoir from the rest of the formation. Specifically here in the US, we're trying to seal off injection from two different locations, right? We don't want any fluid that we're disposing of to reach a US drinking water aquifer, and we don't want it to reach the surface. Those are 2 critical areas that we want to make sure that we don't get effluent into, right? So our containment zone plays a big part in ensuring that it isolates that injected fluid from anything above it. And then finally, we're looking at our overburden. And then again, we're looking at do we have faults that can move? Do we have things that we can impact indirectly through that injection process? So when we're defining our 2 main zones, what are we looking for? In an injection zone, we're looking typically for a higher permeability zone so that we're injecting at lower pressures. And we're looking for typically to try to inject under matrix injection, which is we're not trying to fracture the formation. So we're looking to understand the minimum principal stress. And we're looking to understand the lateral extent that this injection zone has, right? So as the extent of the injection zone increases, I'm able to put more volume into it, but also then I have to understand where that volume or where that CO₂, for example, is going to migrate over time, right? Because when we're looking at CO₂ sequestration, it's not just an immediate process, but it's also the regulator is going to be asking you what's going to happen over 100 years. Where is that CO₂ going to migrate? Is it going to cause any potential harm down the road? So you have to understand where the extent of the area of interest is. We also have a containment zone, and in contrast to the injection zone, the containment zone has to be highly impermeable. So we want high permeability in our injection zone so we can get our fluid in with as low injection pressure as possible. But we want very low impermeability to create very low permeability in the containment zone to create that nice seal above the injection zone. And then, of course, when we're comparing the stresses, we want higher stresses in our containment zone so that even if we were to fracture the injection zone, we would have that containment, and that fracture wouldn't propagate up and out of zone and potentially to the aforementioned either USDW or to the surface. And typically, when we're looking at the lateral extent of the containment zone, we want it to be as laterally extensive as possible. We want it to cover as much area as possible so that we assure that even with long-term migration of fluid, we don't have a risk for that fluid to find a different path to outside of the injection zone, right? So what are the different risks that are associated with injection, right? So there are containment and compliance risks. And when we're talking about a containment risk for subsurface integrity is having the fluid migrate out of the injection zone, out of the assessed zone where you're required to keep the fluid. A compliance risk is then when the fluid is not migrating out, but you're causing, through a poor elastic response, you're causing movement either in the underburden or the overburden of naturally occurring faults, right? So as you start moving these faults, you're going to start getting induced seismicity, which is our first risk outlined here, right? And the induced seismicity, as we'll see in later slides, can be both caused directly and indirectly, potentially by the injection, right? So that would be a compliance risk, but it would not be a containment risk because the fluid hasn't migrated out. The wellbore integrity or the well integrity is looking at damaging the wellbore, and that can both be a containment or a compliance risk, right? If the well loses integrity and creates a path through failed cement to the surface, for example, then that would be a containment. If, for example, you cause enough deformation to where you shear the well and you lose access to the well, that could be a compliance issue. So it can work both ways. With fault reactivation, also can look at it can work both ways. If the faults are linked to the injection zone and you trigger the fault and you cause them to move and you cause them to increase in permeability, then fluid can migrate up it and can move to the shallower horizons. Or if you cause the faults to move and you have well bores that are intersecting those faults, you can cause a shear failure on those faults and then lose access to those wells. So again, could be a containment or compliance risk here. Fracture containment, as the name states, is very much, I am creating a fracture. I want to make sure that that fracture stays contained within the injection zone and doesn't move up into the containment zone or into the overlying overburden. So we want fractures, if we do create them, to be maintained within the injection zone primarily, and in fact only. Surface deformation is again a compliance risk because we're causing variations. We could potentially be causing either uplift or subsidence at the surface, which then can cause potential for equipment failure or other types of issues. And finally, bedding plane slip is very similar to fault reactivation, but instead of causing the fault to activate and move, we're causing the bedding plane to sort of move and then potentially do shear or fail wellbores. And that again is more of a compliance risk. So when we're looking at these, we can categorize them: well integrity, fault reactivation, fracture containment. We would consider those three primarily as containment risks with a secondary compliance issue to them. Induced seismicity, surface deformation, bedding plane slip would be more categorized as compliance risk, right? Where they're still as important, and we still have to manage them, but they don't necessarily mean that that the fluid has migrated out of zone. So that sort of defines what we talk about in terms of subsurface integrity. So with subsurface integrity, how do we monitor, right? So the first thing we have to do is, how do we characterize those risks, right? So with induced seismicity, we typically have some type of induced seismicity monitoring equipment that could be surface-based, surface nodes that are measuring the created vibrations based off of the fault slippage, or they could be well-based and embedded in certain wells where we're listening locally around those certain regions. The well integrity, we're typically looking at monitoring the pressure, temperature, and rate. And through surveillance, pressure transient analysis, step rate tests, we could be looking at specific points in time at what exactly is happening at the well. Fault reactivation, again, we're going to be looking at monitoring the well, pressure, temperature, rate, surveillance well monitoring, the pressure transient analysis, trying to understand where faults are relative to the well location, 4D seismic, INSAR, those types of things can give us a very good idea of how the surface is deforming. And from understanding how the surface is deforming, we can invert that and understand how the deformation looks like in the subsurface or in the layer that we're injecting into. And we have tools to do that, and I'll go through that. For the fracture containment, the main thing we want to understand is what are the stresses. So we're looking at step rate tests, mini fracs, micro fracs within the injection zone to determine the stress. And then in the overburden or the containment zone, we were looking at a leak-off test or a microfrac test. Again, we're going to be monitoring the pressure, temperature, and rate, and surveillance well monitoring, the pressure transient analysis, and any 4D seismic to look at how fluid is moving over time, right? As we're injecting CO2, for example, into a water aquifer, right, or a saltwater aquifer, we're going to be displacing the water with CO2. That's going to have a different seismic velocity and will show up as a different fluid as when we're doing those types of assessments. The surface deformation, very similar again to the fault reactivation. We're going to be looking at 4D seismic. We're going to be looking at INSAR. And the bedding plane slip, we're going to be looking at the injection well monitoring, the pressure, the temperature, the rate, and we're also going to be looking at the 4D seismic. All right. So you'll see that a lot of these tools, a lot of these surveillance tools, and this is by no means an exhaustive list, but a lot of these are repeated and can be used to understand several mechanisms for the subsurface integrity. So what are the inputs that need to get what are the inputs that we need to come up with? And so what you see here, first we want to characterize the pore pressure. That's one of our primary inputs into most of the models that we'll be building to manage this process. In the injection zone, we're looking at pressure transient analysis. We're looking at well tests. In the containment zone, we're looking at either log, and here RMA is our sort of internal rock mechanics algorithm. So that's what RMA stands in. And this is basically our correlations that relate velocities, seismic and acoustic velocities, to material properties such as the modulus and such as pore pressure and such as Poisson's ratio that we can derive from well logs like gamma ray velocities and densities. So seismic is very similar. With seismic, then we're looking at volume-based correlations as opposed to well-based correlations. And you can see then in the overburden or the underburden, we're looking again at log seismic and seismic again. For the mechanical properties, again, you'll see something very similar. We have the logs that we talked about. We have the seismic assessments that we talked about, and we will supplement those with cores, right? So we will have a core testing program where we take samples of the injection zone, we'll take samples of the containment zone, we'll run those through a testing program, come up with modulus, come up with Poisson's ratio, come up with a material property or material evaluation. Typically we're going to be using linear elastic, but we can also go into more complex behaviors if and when necessary. So you can see that's sort of the second column or second pillar here. And then finally, for the stresses, this is probably one of the core areas that we want to be picking up and understanding. And we have a lot of different ways that we can look at calibrating the stresses in the injection zone and then the containment zone and then the overburden and underburden. And you see that the main emphasis in all this work tends to be on understanding the injection zone and the containment zone. This is a little bit different than what we would do in a production scenario. In a production scenario, we'd spend most of our time trying to understand the injection zone, and we wouldn't really care about defining the containment zone that much. But when we're looking at injection and disposal projects, again, whether that's CO2 or whether that's water, we need to understand very, very well both the injection zone and the containment zone. So we will be doing a coring program in the containment zone if we can, and we will be testing those rocks in the lab through a triaxial or uniaxial compaction test to understand the material properties and have those points that we can calibrate our logs to. So that's how the data that we're going to be collecting to understand these problems. And now let's start talking about the different risks that we outlined. So we outlined 6 risks. I think I'm going to cover 4 or 5 of them here, which we typically think are the highest impact the higher impact ones. And the first one is containment, fracture propagation. When you're looking at injecting CO2 in the United States, the government, the regulatory body requires you to stay 10% below the fracture propagation pressure. So you estimate your fracture propagation pressure and you multiply that number by 0.9, and that is your required injection pressure limit by law, by regulation. So how do you define fracture propagation pressure in this scenario? And this is something that's very specific because you can define that number in a lot of different ways. But as it pertains to the regulatory body and what's called a Class 6 permit, that is defined by this step rate test that you see here. And in the step rate test, you're going to start from a shut-in well, and you're going to have equal steps, equal time steps where you're increasing the rate from a minimum to a maximum. Typically, we're doing, let's say, 6 to 7, maybe 8 steps at maximum. And you're trying to understand where the pressure versus rate linear relationship that's established during this matrix injection period moves to a bilinear correlation that's shown here. And the point at which the first line representing matrix and the second line representing fracture meet, that we will define as the fracture propagation pressure. Once we've measured that for the well, we can come back and then multiply our injection pressure limit by 0.9 of that number. Now, from a regulatory perspective, you're allowed to sort of exceed that fracture propagation only during this test to establish the limit. Once you've established the limit, you can't then exceed it after that. And typically these tests are going to be done with water or maybe some viscified fluid and not with the CO2, right? So what we're trying to understand here is what is the difference. If you look at these 2 charts over here, what is the difference between what we call matrix injection and what we call fracture injection? And you see at the top, matrix injection, I understand my minimum principal stress direction, and then I understand fracture propagation pressure. I limit my fracture propagation pressure to be I limit my bottom hole flowing pressure to be below my fracture propagation pressure. If I were to switch this into a fractured injection regime, I would limit my bottom hole flowing pressure based on the stress in my containment layer. And we have a different methodology of determining that, but that would not be relevant for CO₂ sequestration. So for a fractured injection, I would be greater than my fracture propagation pressure, but below my the stress in my containment zone with some safety factor. So what's interesting then is that it's not a one and done, right? We are injecting, we are changing the pore pressure, and so we need to account for those changes in pore pressure with time, right? So I have in the middle chart here, I have an initial pore pressure, which is outlined by this blue line here, and that corresponds to an initial minimum principal stress that's outlined by this red line here. And you can see that I've intentionally put a higher stress value in the containment layer and in the underburden in comparison to the injection zone. But as I produce or inject, I'm going to change the pore pressure at least within the region or within the drainage region of the injector or producer. So if I were to produce, I would see depletion, I would see compaction, the pore pressure would drop, and the stress would drop as well. Typically, the stress will drop at a lower rate than the pore pressure. So based off of your material properties, that can be anywhere from 0.4 to 0.8 psi lost per every 1 psi of pore pressure. So as I'm thinking about these injection pressure limits that we established, and what is my fracture propagation pressure, I also need to be thinking about this. Am I producing more from this zone, or am I injecting more into this zone? And how is that impacting the pore pressure? And how is the pore pressure impacting the fracture propagation pressure? So you can see here the thought process. I'm reducing my pore pressure, therefore I'm reducing my total stress, therefore I'm reducing my fracture propagation pressure, and therefore I need to reduce my injection pressure limit. Also here, as you can see, I'm increasing the potential for containment in this scenario, because this red line now, this stress line over here, is further away from the containment layer stress. So that's a good thing, that promotes containment if I were to fracture this formation, which again I'm not planning to. So from there, I have the other scenario, which is increasing the injection pressure. And for increasing the injection pressure, the opposite effect happens, right? So I increase the pore pressure, I increase the total stress, I'm going to increase my fracture propagation pressure, and therefore I'm going to increase my injection pressure limit accordingly, but I'm going to reduce my containment window, right? So I have to be a little bit careful in this scenario. Yes, I'm getting a plus, I can inject at a higher pressure, but I also need to be aware that the level of risk might be a little bit higher if I were to get the injection pressure limit wrong. But so understanding that and moving forward, that is important. So you can see I've outlined here in red that this is typically the scenario that we're going to be under when we are injecting for disposal. We're going to be dilating, we're going to be overpressuring the reservoir. So thermoelastic effects, impact of temperature, that's the second thing I have to take into account, which the temperature of the CO₂ will likely be lower than the temperature of the injection zone, and therefore the stresses are going to be reduced. So again, we're going to have some type of compaction in the injection zone, and we're going to have some type of cooling. So here I'm going to be reducing my total stress. I'm going to therefore be reducing my fracture propagation pressure, and therefore I'm going to be reducing my injection pressure limit, but I'm going to have an increased containment window because I've reduced that stress, and I've created a larger difference between the containment and the injection zone. Okay. On the other side, if I were to be injecting a hot fluid, typically that happens when I'm producing from a deep reservoir, and then I'm going back and I'm injecting into a shallower reservoir. without changing the temperature of the fluid. In doing so, then I'm going to be increasing the stresses in the injection zone. So I'm going to see an increase in the total stress. I'm going to see an increase in my fracture propagation pressure, which is positive that I'm going to see an increase in my injection pressure limit, but then I'm increasing my risk because I'm reducing that containment window between the stress in the injection layer and the stress in the containment layer. And something very quickly here to think about is, how does the injection layer cool? How does the containment layer cool? So typically the injection layer is going to cool through convection because I'm moving fluid into that injection zone. So I'm displacing hot fluid with cold fluid. So it's going to change temperature faster. Therefore, it's going to change stresses faster. The containment zone is typically changing through conduction, which is a much slower process. So I need to take that sometimes into account if I'm going to be injecting for extended periods of time without necessarily shutting in the well and allowing some of that temperature to equilibrate. So sometimes I also need to be considering what's happening from a temperature perspective in my containment zone. And that tends to be sort of something that as an SME, you need to sort of test and see how that is going to impact your operating window. So moving on, we talked about fracture containment and we talked about setting injection pressure limits. So we're going to look at the second cause of loss of containment here, which would be the subsurface faults and the ability of those faults to migrate fluid up and down them. So in this sense, we have to first define that we typically are looking at three different types of faults, right? And the three different types of faults come with three different stress sequences, right? So typically here you will define your overburden stress, which is your vertical stress, and you'll define two horizontal stresses. And that's typically a fair definition of what we consider to be the principal stresses in most cases. And the principal stresses being the vector stresses or the direction of stresses where you don't have any shear, right? Now, in some cases, we would have a salt, or we would have some type of geological body that would cause stress rotations. But in most cases, we can be very sort of general here and say they have a vertical stress and we have two horizontal stresses. So in a normal faulting situation, think of you're trying to pull the earth apart, and so you cause a failure and you cause a fault slippage. And in those types of cases, the maximum stress is typically vertical, and the two horizontal stresses are typically lower than the maximum principal stress. And opposite to that, you have a thrust fault. With a thrust fault, you're typically trying to push the earth towards each other, and that's what creates the failure. In this case, the horizontal stresses tend to be greater than the vertical stress. And the final case is the strike slip. And in the strike slip, you have basically the fault is caused by shearing in sort of the direction in and out of this screen here, right? And in this case, you have the vertical stress sitting in between the two horizontal stresses, where you have that failure because you cause the earth to move laterally as in contrast to the other segment. And what you can see here is, when we're looking at normal thrust faults, you can see that we'll have an offset in the formations, while the strike slip fault may not necessarily show that much offset between the different sides of the fault. Okay, so that sort of defines the faulting regime and defines the stress regimes. So once we have identified the faults that are acting in the subsurface or acting in the region of interest, we want to understand whether these faults are critically stressed, as in they are just about to fail, or that they are non-critically stressed and they're far away from that failure envelope. there's a lot of different failure envelopes that we can look at here. So what you can see here is a cross section through the earth. You have all these through the subsurface, and you have all these different faults that we need to assess for stability. So if we look at these faults, we can create a understanding of the stress state at the faults and compare it to what we call here, for example, is a more Coulomb failure envelope, where we have some type of friction angle and assuming zero cohesion in this specific case, and we're comparing that friction angle to the stress state on the fault. So in this initial stress state, before I start doing anything to the field, you can see that most of these points are in blue. They're well below the failure envelope. Now, this may or may not be the case in all geological settings. As we move for example, as we move into California, we would tend to think that a lot more faults are critically stressed even before we start doing anything. As we move towards more passive basins like the Gulf of Mexico and the region around the Gulf of Mexico, we would tend to think that those are much more passive, and most of the faults are non-critically stressed. But as we start injecting or producing, or we're doing different things, we can start changing how what this Mohr circle looks like and what the stability of these faults look like. So you can see over here we have a case here where we're changing the pore pressure. And in this case, we have two faults that start to light up and say, okay, these faults, if you move them into this increased pore pressure, and you reduce the effective stress, right, which is what we're plotting here. So when I increase pore pressure, I increase the total stress, but I reduce the effective stress, right? Because if you recall in an earlier slide, we talked about for every 1 psi of pore pressure change, I have 0.4 to 0.8 psi of stress change. Therefore, as I increase pore pressure, I increase the total stress, but I reduce the effective stress on the rock, which is what I'm concerned with here when I'm looking at fault stability. We can also have cases where we change the friction coefficient on the fault. It's not something that we're always very good in understanding, even what the initial friction on the fault is. But if we were, for example, to start lubricating and having fluids move in and out of the fault, that could change the friction coefficient, and then that could lead to failure. We could also be changing the stresses while maintaining the vertical stress as it is. For example, we're reducing or increasing the minimum principal stress in this case, and that could also lead to failure and causing things to move into the critically stressed state. And this is just for visualization, but please note that nothing can move past the green line, right? So once the stress state reaches the green line, it'll stay at that green line, and then the fault will start to move, right? It's only in models where we assume that the fault is not moving that these red points can move beyond the green line. But in models where we're allowing the faults to slip and move, then everything gets to the green line and stays at the green line, and you then have relative movement of these planes against each other. So we talked about what types of faults we have. We talked about how these faults move, and now we're just going to talk about what happens when they move, right? So I start off with a fault, I start stressing it over time, and you can see that as I stress it, it deforms. At some point, it's going to rupture. That's going to cause that induced seismicity in the subsurface. And then after it ruptures, it's going to relax, right? So what happens when we start injecting is we could potentially change the rate that we're loading or the load that we're applying. And so the faults respond to two things. They respond to the overall stress change, and they also respond to the rate of stress change. So that's sort of important to take note. I have a lot more, but I think I'll try to end with the fault stability, with the induced seismicity, and then I can stop for questions. So just to note here, there are two types of activation events, right? If the fault exists within the injection zone, that could be referred to as a wet event, where I cause the faults to slip in that injection zone, and therefore they create that induced seismicity signal. Or it could be a dry event. So when we talked about why do we need to consider the underburden, what's happening in the underburden, right? We're just worried about fluid moving out. But also if we have faults in the underburden, by changing the pressure in the injection zone, I can cause those faults to slip and I can cause some movement. So in general, I'll try to, maybe I'll end with this slide. So our workflow for assessing induced seismicity starts with having a reservoir model, and I'm cross-referencing that model with the pore pressure that I'm measuring at different wells. And then that data moves into a mechanical earth model. And the mechanical earth model is very similar. It contains the reservoir, but it also contains the different layers that we talked about, the containment, the overburden, the underburden. And from that, I can assess what the surface deformation looks like, and I can calibrate it to the surface deformation. And then finally, I take the stresses that are generated from that mechanical earth model, I put it into my induced seismicity model, and I can then assess the seismicity rate with a very wide sort of probabilistic range, right? Because this is a lot more empirical, and if you talk to anybody that does induced seismicity, we're not predicting induced seismicity, we're evaluating the risk. And I think I'll stop there. I have more slides, but maybe allow for maybe 4 minutes of questions if folks have. I don't know. Mayara, what are your thoughts?
Yes, we should stop. But thank you so much for this great informative session and for your time and effort as well.
Oh, no problem. Thank you.
Okay, so for a quick Q&A session, uh, for the first question, okay, can real-time wellhead pressure and PHP data be used for anomaly detection via AI to prevent out-of-zone CO2 migration?
That's a good question. I think but pressure, whether that's wellhead, so obviously bottom hole flowing pressure is much more valuable than wellhead pressure. Typically, we assess pressure to be a lagging indicator. So by a lagging indicator, it tells us, hey, something strange has happened, right? So if there are changes in the pressure response, then we can go back and say, hey, there could be a problem here, right? As opposed to a leading indicator, which is something that tells us there could be a problem in the future. Now, again, it's very important to have that understanding of the pressure, so that if something does happen, you can catch it very quickly and have enough time to respond to it. But it's not necessarily preventative, but it's informative. And can you then have that as part of a AI or assessment? For sure, that's definitely things that we're working on, and I have some more slides that sort of look into our monitoring program and how we have those types of indicators, and how we use different algorithms to flag wells and flag risks on certain wells.
Okay, thank you. And another one is, how do you determine and validate the fracture propagation pressure in practice? And how conservative are your operating margins below it?
Okay, so for the fracture propagation pressure, basically you do a step rate test, and that's how you would validate the specific value in the field. What we would tend to recommend is to do that step rate test on a periodic basis to then account for the changes in pore pressure and temperature that we talked about, because the reservoir or the injection layer is evolving in time. So a step rate test is what we would typically rely on as our primary source. If we can't get a step rate test, then we were looking either at model-based assessments, whether that's through looking at logs, whether that's this workflow that we have over here, where we're coupling the reservoir model with the mechanical earth model to predict how the stresses are changing over time, and then have an assessment from the stress to the fracture propagation pressure. What are the limits? The limits are usually specified from the regulatory body. So in the United States, it's 0.9. In certain states, for example, California, it's 0.8 of the fracture propagation pressure. In other areas of the world, they may use slightly different numbers.
Okay. Thank you so much, Mr. Karim, again. And I'm quite sure we all benefit from this session.